So what did we just do? It was kind of a lot, so let's recap together. First, we defined two competing hypotheses. After the speech, 60% of voters support Melvin, and our alternative is after the speech, support for Melvin among voters is no longer 60%. And then we simulated what would happen if the null hypothesis were true. In other words, we imagined that Melvin's support is holding steady at 60%, and we repeated the poll again and again and again. So before we kind of just showed you this magic distribution that appeared out of nowhere, that was what would happen if our null hypothesis were true, and we repeated the poll again and again. And here, I want to show you a simulation, means something made with the computer that gives some insight into what it is that we're actually doing to, generate that distribution, what it is that is behind that. So this picture shows that we've got a population, and that is all the animals in town. And then the way that a single poll works is that we take a sample. So we randomly select some folks in the population to be part of the poll. And we figure out how many of them support Melvin. And then we drop that onto this chart on the bottom. So we've run one imaginary poll so far, and we've got one result, and it came out between maybe 65%. And we can do it again and again. And we can keep doing it. We just do this so many times. Look at that. And then over many, many, many repeats of this procedure, this curve emerges. So I'm just going to do that one more time just to show you what it was. One poll, two poll, and then more, again and again and again. And we can draw this curve over it, right? So we've only done it a finite number of times, so it's kind of a little bit jagged and imperfect. But if we did this infinitely many times, which is something you can't do with a computer, but you can do with some algebra and some math, and mathematicians have worked this out for us happily. So we get this curve. And so that is where our distribution of what would happen in the null world came to be. That's just a little bit of a story behind it. And then we defined a range of outcomes that would be unsurprising if the null hypothesis were true. We shaded the middle 95% of this distribution, and then we consider anything that happens inside this shaded range is not going to be surprising. We don't think it's surprising or particularly interesting if the null hypothesis is true. And then we checked if our observations were in the unsurprising range, and they fell outside of it. So we're saying, if the null hypothesis were true, that would be a little bit surprising. So we decided if our results were compatible with the null hypothesis. We go back to our two competing hypotheses, and we say, well, because of our results are surprising enough in the null world, we're going to say we reject this. We cross this out. So what does that mean? Should Melvin be doubling down on his egg strategy? We're not going to answer that immediately, but I want to put this question in your mind right now to think about over, the next few lessons. Are you convinced? Does this mean that he needs to be all in on the egg strategy that was that he promised at his speech before the last poll? Or would you need some more evidence? And why do you think that is? So just think about this, put this in the back of your mind for now. But I also want to show you how this all relates to science because of, as much as I'm sure you're invested in Melvin's mayoral candidacy, you probably are here because you want to learn about science. And I assure you that, this is a method that is widely used in science. So here's an example. What if we were interested in studying if a new drug helps patients, right? So we've got people that maybe are suffering with a medical condition, and we want to understand if a new drug is useful for them. So maybe it's easy, right? We could just compare outcomes in patients with and without the medication. Well, is it that easy? Okay, let's think about what would happen if we just did a simple comparison, no hypothesis testing at all. So here's our thought experiment. We're going to monitor 100 people who share a medical condition. And let's say that no one is taking the new drug at all. We just have 100 people. We're just going to observe them. And we're going to randomly split those people into two groups. right? There's lots of ways that we could split them, but we're just going to randomly split them up, see who falls into which group, and we're going to monitor those groups. And we're going to have everybody in them rate their symptoms from 1 to 10. So we've got maybe a survey scale that is widely used for studying this condition, and we can have everyone rate their symptoms, and then we're going to average the ratings in each group. Now, the groups are likely going to have different ratings, right? And so we'll just say that a higher number means symptoms are more severe. So this group on the left has on average, more severe symptoms than the group on the right. Now, why do you think the ratings are different? Nobody has been given any medication whatsoever, right? Well, this is actually quite expected if you just randomly split people into groups because, some people will just have more severe symptoms than others, or some people, might feel, like they kind of hide, they don't report the true severity of their symptoms on a survey. People have all different ways that they could, experience this, and not everyone is equal or identical here. So, if we just randomly split people, it's often just going to happen that one group is different in some way by chance. So now imagine we were to give a useless medication to one group, right? So this is a medication that does nothing. It's a sugar pill maybe. We give it to this group over here, but not to the other group. We actually shouldn't be surprised to see a difference in how the groups rate their symptoms, right? So now if we saw this difference here, even though this group is lower that has the pill, it has nothing to do with the pill. It's just because of, when you split groups, they're not going to be perfectly balanced in every way with a finite number of people. It just happens. So in this case, the presence of a difference isn't interesting at all. So if we were to give people a medication and say, well, the group with the medicine is lower, that's not actually very convincing, because how do we know that difference isn't just because of the way the groups were split? And if we had split the groups a different way, it might completely go away, right? So we're seeing a difference even though the medication does nothing. So significance testing is a way of asking, if nothing interesting was happening, how surprising would our outcome be? So if nothing interesting was happening, right, this is our null world. So if support for Melvin had stayed the same in the polls, or if the medicine truly does nothing, we want to ask, how surprising would our new poll result, or the difference in how groups rate their symptoms, how surprising would that outcome be? And I really want to, if you remember nothing other than this, we're really talking about surprise when we talk about significance. People bring a lot of baggage from the world about what significance means, but it really has to do with how surprised we would be assuming that the null hypothesis were true, assuming that the world were proceeding as normal and absolutely nothing interesting was going on. So significance and surprise are, two words that I think, if you can try to, in this context, take the word significance and move it away from concepts like important or major or big, right? And just kind of link it closer to surprising, right? This is the way that, it can help to develop your intuition about significance. So coming up, we're going to explore some limitations of hypothesis testing. If only, I'm sorry, I wish it were like that. Now that I've shown you this, you know exactly how to prove definitively that something is true in the world or not. But there really are a lot of interesting and nuanced limitations. And they're really important because some of these limitations, we can forget about them because of the way that we speak about hypothesis testing, in the world, or how it comes through in the news. So we're going to explore some of the limits and the nuances and things that make it really interesting and kind of a meaty topic.